Continuing on with our circle unit, we're going to take a look at, review a little bit of the inscribed angles and our central angles, but also connect it to different chords and arcs in the circle and see how they connect. So this first question, a little bit of review. Center of the circle below is circle O. If angle B has a measure of 15 degrees, we have to find X and Y. So angle B is a inscribed angle. The vertex of that angle is sitting right on the edge of the circle. So I know an inscribed angle is equal to half of the arc. So I could say the measure of angle B is equal to 1/2 arc AC. So that little M with that arc symbol saying measure of arc AC. So if I know angle B is 15 and I'm trying to find that measure of arc AC, I could think divide by 1/2 or multiply by that reciprocal, and X has to be 30. Okay, that's the algebraic way. If you can just think the arc is double the angle, well, then you got that probably a little bit faster. Going on to Y, trying to solve for Y, if we remember back, we said, well, these are both radii, which makes this triangle an isosceles triangle, which would tell me that those two angles, Y and 15, should be equal because they're base angles of an isosceles triangle, and base angles of an isosceles triangle are congruent. If we go way, way back to the beginning of the year when we looked at our exterior angle theorem, and thinking about this as a triangle, the exterior angle of a triangle, angle X, is going to be equal to the sum of the two remote interiors. So I would also know, just an extra, X should be equal to Y plus 15. So if I knew that X was 30, that would give me a different way to solve and also show me that angle Y is 15. Okay, moving on, taking a look at this next problem. So we have triangle ABD was reflected across diameter BD. So if that's a diameter, I know the center point's on the circle somewhere on that line. And it's creating a kite. Now a kite, going back to our quadrilateral unit to remind ourselves what a kite was. A kite was a four-sided figure where we had two sets of congruent adjacent sides. The diagonals, I would have one that would bisect opposite angles. So this line, our diameter line actually in particular, I will know from our kite properties, would bisect opposite angles. Now they're not equal, meaning like this top angle and the bottom angle are not equal. However, I would know that they would be bisected. So I'm having issues with my marker today. Okay, so if we're taking a look at angle BDE, so angle, I'm sorry, and they also told us angle ADB is 40. So ADB is 40. And first thing that we need to find is angle BDE. So BDE is the one right next to it, and we just said that those two angles would be congruent, just from using properties of kites. Angle BAD. So angle BAD is sitting over here. And because I know that this is a diameter, BD is a diameter, and A is an inscribed angles are half of their arcs. And we also said inscribed angles opening up to a diameter would be 90 degrees, always forming that right angle, which should make sense. Reminder, if that is a diameter that cuts your circle into 180 degrees. So I would know that that angle should be half of that arc. Moving on to angle BED, well, we're going to notice the same thing. BED is this angle sitting here, opening up again to a diameter, which an inscribed angle is half of the arc, or an angle opening up to a diameter is always a right angle. Angle ABD, so this is this top angle of the triangle. Well, it's a triangle. So we have 180 degrees in a triangle. We know one is 90. We know the other is 40. So that's going to leave us with 50 degrees for this angle. And using, again, our properties of kites, knowing that that diagonal would bisect the angle, angle EBD should be the same. I can also find EBD by doing the same thing that we just did using our triangle properties. And now angle ABE. So that's just saying let's put these top two angles together, so that's really taking that 50 plus 50, and that's getting us a total of 100. And then angle ADE, so on the opposite side over here, same idea. It's saying let's take our 40 plus 40 and set that equal to 80. So that kind of gives us an interesting property here. If we take a look, we have an inscribed quadrilateral, meaning all of the vertices are on the circle. And I'm looking at these opposite angles, the ones that we just found. These two are opposite angles of an inscribed quadrilateral. And if I take a look at the sum of those two, the sum will equal 180, and that's going to be an always case. They will always equal 180 so long as that quadrilateral is inscribed in a circle. If I maybe try and take a look at y, taking a look at that angle and looking at this arc, okay, and then if I take a look at the opposite angle, so here's our opposite angle, and they're both inscribed angles, and I take a look at that arc, we should notice that those two arcs, that blue arc and that red arc, put together equal 360. And if they're inscribed angles, I know inscribed angles are half of the arc. So half of 360 should always give me that 180 degree property. Okay, moving on. So we're going to take a look at now chords. Chords and arcs and angles and see how they're all connected. So it says in a circle or in congruent circles, congruent chords are equidistant from the center. And we can take a look at something called the converse. It's just doing the opposite. It says the circle or in congruent circles, if the chords are equally distant from the center, then I know that they are congruent. So the way that we measure distance, either you're going to see that they're going to be marked congruent with those lines, or you're going to see that perpendicular line, that right angle marking. So if they're this measuring distance away, I see measured with that right angle. And I can see here on this example, these two have the same distance away from the center because the lengths are marked congruent, and it's a distance because it's a right angle. So what that tells me then is this top chord has to be equal to this bottom chord. Okay? So this little section here is worth 3.5. So that means this other section here is also worth 3.5 since it's bisected. We're going to actually look at that property in a second. And if I put those two together, that's going to give me a total chord length of 7. Now, since they are equally distant from the center, then that means this other chord must also be a length of 7. So if the chords are the same distance from the center, then they're equal, and vice versa. If the chords are equal, then they're the same distance from the center. Okay, so our next page. So we have in a circle, or congruent circles, congruent chords have congruent arcs. Okay, so if I know the chords are the same size, then I know the arcs across from them are also the same size. Now, it doesn't mean that if this chord has a length of 5, then the arc's a length of 5. Be careful. That means that as long as I know that the chords are the same size, then whatever the sizes of the arcs, they would be the same. So in this case, I don't know how big the chords are, but I know that they're equal because I can see their marking. So what that's telling me is that these arcs must be equal. Here's an arc of 74, so that means x must be 74. Okay. Looking over here, I have a diameter. I can tell it's going through the center. And I see a couple of chords marked equal. So what that's telling me is that if the chords are equal, then I know their arcs across from them are also equal. So I'm just going to use half this circle right now, since I know that half of a circle, all of those arcs should total 180. So if I remove what I already know, which is 88, I'm going to be left with 92. And that 92 degrees needs to be split up evenly between these two arcs, or I'm sorry, yes, the arcs, because I know the chords are equal, so I know the arcs are equal. So if I divide that 92 in half, we're going to find each of these arcs must have a total of 46. And again, I know they're equal because the chords were equal. So since I know these arcs are 46, and I know that this chord has the same length as this chord, then that means this arc must also have the same measure as these arcs. Okay, so now that brings me to the other side of the circle, which again, I still have 180 degrees. And if I remove that 46, now I'm left with 134. And again, now these arcs are marked congruent. So if I'm trying to find x, that means I should be able to divide that in half. And when I divide that in half, I'm going to get a total of 67. So that would tell me x must be 67, and that arc must also be 67. Okay, so if the chords are equal, the arcs are equal, and vice versa. If the arcs are equal in measure, the chords would be equal in measure. Okay, a little bit more with chords. What if we have parallel chords? Okay, well, parallel chords will also give us congruent arcs. So for instance, over here, I could tell you arc AC is going to be congruent to arc BD because I know that these lines here are parallel. Okay, so if we look at 5, it says in a circle shown, we have parallel lines. So BC is parallel to DE. So automatically that's telling me, if I were to just look at this, I know the measure of arc CE is going to be equal to the measure of arc BD. Okay, they've told us BC, arc BC is 58, and the measure of arc DE is 142. And we have to find this angle. That's really what we're looking for. Well, it's an inscribed angle, and I know an inscribed angle is half of the arc, so I need to figure out this arc measure. And I know this arc is equal to this arc. And if I put them all together, I have 360 degrees in a circle. So we're going to remove what we have just to see what's left over. Taking that 360 and removing what we have, I have 160 degrees left over. That has to be split up evenly between those two arcs. So if I split that up evenly, that's going to give me a total of 80 degrees. So that means arc CE is 80 and arc BD is 80. Now if I'm trying to find that angle, angle CFE, being an inscribed angle, is half that arc that it opens up to, which is 80. So that's telling me that angle must be 40 degrees. Okay, a couple more theorems we get here. And I'm hoping that you're looking at this and saying, wow, these all seem really kind of similar. They're all connected. So these next two are very connected. So it says in the same circle or congruent circle, if I have congruent central angles, well, then I know their arcs have to be equal. And that should hopefully make sense. If I know a central angle, I know a central angle equals its arc. So let's say that angle is 40. So that arc has to be 40. And if these angles are equal, well, those arcs have to be equal. So hopefully that should make sense. Okay. But now if the arcs are equal, think about what we said. If the arcs were equal, the chords were equal. So if I'm looking at this next theorem, if I have congruent circles, if I know I have congruent central angles, then I'm also going to have congruent chords. Okay, so if I put this all together, if my central angles are equal, the arcs are equal, the chords are equal, I get a whole big bunch of equal properties here. Okay, so looking at this next one, I have to find the measure of angle 1 and angle 2. Okay, well, I see two congruent chords. If my chords are equal, the arcs are equal. So if that's 50, this arc over here is 50. And I can see the measure of angle 1 being a central angle, so the measure of angle 1 is equal to the arc, which is equal to 50. And that triangle being isosceles, that means that these two base angles, angle 2 and the other unmarked angle, they have to be equal. So again, if I take 180 and I subtract out the angle that I know, I'm left with 130. And if I divide that by 2, that's going to leave me 65 for the measure of angle 2. Keeping in mind, that's because that triangle is isosceles. And if it's isosceles, then we know that the base angles are equal. Okay. And then this last theorem that we have here, this is kind of going back to that first problem I said we'll get to a theorem later. Here we go. If a diameter of a circle bisects a chord, then it must be perpendicular to the chord and vice versa. If the diameter of a chord is perpendicular, then it bisects it. So it says in the figure, AB is 10. And keep in mind, AB is a radius of your circle, so that means all radii of the circle are 10. AC is a chord, and they're telling us this whole chord is 16. And then we get that BE is perpendicular to AC. So what we've just learned, if this is perpendicular, that's going to take our chord and cut it in half. So our job is to find DE. Notice DE is just this little part right here. We have a right triangle. Triangle ABD is a right triangle. We could solve at least for that little section, I'll call it Y, by doing the Pythagorean theorem. So 8 squared plus Y squared is equal to 10 squared. If we solve, we're going to have 64 plus Y squared equals 100. I subtract over the 64, so I'm going to have Y squared is equal to 36. So that means Y must be 6. Keep in mind, we're only taking that positive answer because I only have a positive distance. Okay, so if that answer is 6, remember what we're trying to find here. We are trying to find the length of just segment DE. But we know from B to E is a radius. Okay, so if I were to put these little segments together, that little segment BD, and add to that segment DE, I'm going to get that whole radius BE. Okay, and let's fill in what we know. Well, I know that this little part BD, we just found that, that's 6. I'm trying to find DE, and I know, again, BE is our radius, that's 10. So by knowing that, subtracting over that 6, I can tell you DE must be a length of 4. Okay, there was a bunch of chord properties, angle properties, kind of putting everything together. We're going to practice this in class. Hope this kind of just gave you a foundation so we can roll with this in class when I see you next. Okay, have a great day.